Gillis here with the final lab, Lab 5 on inelastic collisions. You can choose anything to analyze for this lab using prior knowledge, idle, and trackers. Since we have done a lab on everything that we've learned so far except collisions, I've chosen to do my Choose Your Own Adventure lab on collisions. My adventure was to analyze the motion of a maximally inelastic collision between a moving car and a stationary car. The point of the lab was to analyze real video's data to quantify a collision and then to compare the findings with the model in VPython to determine if momentum is actually conserved and to see how the energy is transferred. The main result was the observational data fit the model and the momentum was conserved. There was a loss in kinetic energy, however, this is due to not accounting for frictional force, but for all intents and purposes of our classroom, frictional force is negligible. The relevant systems and models in this lab are the momentum principle, which is equal to net force times the change in time. During the collision, there is zero net force. Therefore, the change in momentum is also zero, and momentum is conserved. The energy principle for maximally inelastic collisions shows that the final kinetic energy is not equal to the initial. The change in the internal energy in the system can be accounted for in a loss of heat, vibrations, or transformations. From the information we see, the following equation can be used to calculate the change in the internal energy, or delta E internal. For my observational data, I chose a video that I found on YouTube because it models two cars that exemplify a maximally inelastic collision. This allowed me to track and analyze motion to get real data for my lab. First, I tracked the motion of one car alone, then the second car alone. After they came together, I tracked that motion as well as using the combined center of mass. Here's the video after tracking. I chose the origin to be the initial position of car 1's center of mass. The calibration length is set to be 0.25 meters, or the length of one car. On the right here, you can see the data of car 1, car 2, and both cars together. Using the data on the right, I made two CSV files in order to read them into the code, which I will show later. Both of these files have the X and Y coordinates for each car. Shown here on the position v time graph, you can see the velocity of the center of mass for all three scenarios is constant. Car 1 moved approximately 1 meter per second initially. However, after hitting car 2, it moved approximately 5 meters per second. Car 2 was initially at rest until after the collision when it moved up 5 meters per second. So we can see here that the combined velocity was in fact 5 meters per second. Now, let's analyze the computational model that I created to model this adventure. The two code blocks here I read in the data from Tracker of red car 1 and blue car 2 in order to compare them in the model movement to be created. All initialized values can be found here. 4 objects for the computational model and 2 for the experimental model. These fixtures represent the tracks on which the car will be moving. I initialized the mass of the cars here as well as their initial velocities. Here, we have additional initializations. V is for the velocity and P is for the momentum. The kinetic energy of both cars is shown here using the formula for translational kinetic energy, 1/2 mv squared. The total kinetic energy is the sum of the two. The while loop shown here is used to update the position of the cars when the code is run, and the model appears, the observed motion appears at the top, and the model created by the computational model is shown below. At first, only one model is moving, while the other is at rest. After they collide, they get stuck together and move at a different velocity, just as minimally inelastic collisions do. I printed the final velocity of the cars combined. This is approximately half the initial velocity at 0.53 meters per second. Next, you see the change in momentum, 0. Lastly, you can see the change in internal energy, or 0.081 joules. Using the loss of energy, I used the equation of the final kinetic energy of the two minus the initial kinetic energy of the two to find that. Here, the computational model moves farther than the observed model because the model does not account for friction. The values given by the model differ from those given by calculated observed values. If you look at how each of the values are calculated, you can understand why. For the observed motion, the initial momentum of the total system was 0.3 meters per second. The final is 0.29 meters per second, which shows that the momentum was mostly conserved with only 0.01 difference. Even though their velocities were different, this shows that the momentum was conserved with a 3% error. This fits the model data which had a value of 0 for the momentum change. The calculation for the change in kinetic energy shows that there was a loss of 0.089 joules based on the observational data. However, this difference is because the model did not account for the frictional force, and another main error was due to the inaccurate placement of the center of masses in tracker. Going back to the main result, you can now see that the kinetic energy and overall energy changed. Kinetic energy was lost and the momentum was conserved during the collision. Answering questions. Question 1. The reason why you can tell that this is a minimally inelastic collision is that the two cars stuck together after they collided. This is for sure because the cars were magnetically attracted to each other at the ends. The change in kinetic energy is not equal to 0. Question 2. Yes, the reason for getting 0.01 kilogram meters per second is because of not precisely pinpointing the center of mass on tracker. In reality, momentum is conserved when two cars collide. The momentum was properly calculated with only 3% error, and a reduction in this error would require perfect placement of the center of masses in tracker. Question 3. If the model was run again, the observed motion and the computational motion models would both move the same distance in the same exact way.